Hi, this is Swagat from University of Nottingham. I'm a postdoc there, and it's such a pleasure to talk about this work today at this conference. This is a work which appeared in early February this year, done in collaboration with Professor Varun Sani at IUCAA in India, and talks about canonical and non-canonical inflation in light of the recent CMB data release. To start with, over the past few decades, we have strengthened our standard scenario of the universe. For example, flat lambda CDM is like a toy model in the standard scenario. And the standard scenario describes the evolution of the universe, both at the background as well as perturbation level, reasonably well for the past 13.8 billion years. The standard scenario is based on two types of assumptions. One of them has to do with assumptions on the presence of two new components as composition of the universe, as well as, which is more important for this talk, on special initial conditions at the beginning of this hot Big Bang phase. They're in the form of spatial homogeneity and isotropy over large angular scales in the early universe, spatial flatness in the early universe, as well as particularly the presence of almost scale invariant adiabatic and nearly Gaussian fluctuations as initial conditions for all structure in the universe. Now, for example, if we stare at the CMB map, we see nice temperature fluctuations, similarly polarization fluctuations, and we can ask this question, that what created these fluctuations? And the leading hypothesis is that cosmic inflation, which is a transient period of rapid accelerated expansion in the early universe prior to the hot Big Bang phase. And this cosmic inflation actually sets natural initial conditions for the hot Big Bang phase. Now, inflation has two types of dynamics. One is the background dynamics overall. And during during inflation, the background evolves as almost quasi-exponentially. So it's a quasi-de Sitter space which sort of addresses the horizon and flatness problem, which is still debated. But what is more important for today's talk is that inflation provides linear fluctuations. Linear perturbation theory during inflation provides a natural mechanism for seeds of all structure in the universe, including CMB fluctuations and large-scale structure. So we'll talk about it a bit one by one. In the background dynamics, so what we think, our system is a simple single scalar field, which is minimally coupled to gravity, and our gravity is GR in this talk. Yeah. So the scalar field comes with some kind of a self-interacting potential, and as the scalar field rolls down this potential, the universe can inflate if twice of the kinetic energy of the scalar field is smaller than the potential energy. Okay. So early times that's satisfied for many potentials. And at late times, the inflaton field rolls faster, and then inflation ends, and later it reheats the universe into the hot Big Bang phase. So in this regard, we have to introduce two important parameters. One is the first slow roll parameter, which is the rate of change of Hubble divided by Hubble square. As long as this is smaller than 1, which just tells you that twice of kinetic energy is smaller than potential energy, the universe actually expands in an accelerated way. The other thing that we need is the second slow roll parameter, eta h, which guarantees that inflation happens for some prolonged period, which can then address the problems of the initial conditions of hot Big Bang. So there are these two parameters. Usually, for most of the potentials, during inflation, the dynamics enters into something which we call the slow roll regime. And in the slow roll regime, both the slow roll parameters are much, much smaller than 1. And in this slow roll regime, there exists attractor background solutions, and this leads to a quasi-de Sitter expansion of space, so almost exponential expansion of space. And that sort of addresses the background initial conditions for the hot Big Bang. But what's more important are the generation of perturbations during inflation, which are basically quantum fluctuations of light or massless scalar fields, which can be seen in macroscopically large length scales or on super Hubble scales, basically. So the system is, we have a GR and we have a scalar field. and it's minimally coupled to ZR. For example, here I've shown a canonical kinetic term. Later, I'll talk about non-canonical kinetic term. Anyway, in such a scenario, there are two gauge invariant in the first order, two light fields that are guaranteed to exist. The one is the co-moving curvature perturbation, which is a combination of scalar field perturbation and the metric curvature, 3D curvature of the metric. These fluctuations, scalar fluctuations, later see the temperature fluctuation and density fluctuations in the early universe. And then there is transverse stressless tensor fluctuations, which later become relic gravitational waves. So all these fluctuations during inflation are created in the sub-Hubble scale, and they are stretched outside the Hubble radius during inflation, where they remain frozen, and later they enter in the hot Big Bang phase, and as they enter, they create fluctuations for the universe. So in that sense, we can think of the universe as acting as at least two computers. There are some reasonable initial conditions which goes into inflation, and inflation evolves them and gives us natural output, which are inputs for the hot Big Bang evolution. And then we can evolve it either to CMB, to study CMB, or to study CMB fluctuations, or to the large scale structure, which is the standard scenario and well known. And the power spectra of scalar and tensor fluctuations in the slow roll regime, slow roll inflation, they take the form of power laws, which have some amplitude and some scale dependence. Usually these spectral indices are measured around the CMB pivot scale. The amplitude of scalar depends on Hubble as well as slow roll parameter. The amplitude of tensor purely depends on the Hubble scale during inflation. The scalar spectral index is actually a combination of both the slow roll parameters, while the tensor spectral index only depends on the first slow roll parameter. And the tensor to scalar ratio, which is an important quantity, depends on the first slow roll parameter. And there is a consistency relation which relates tensor spectral index to the tensor to scalar ratio in this slow roll design. Okay. Now, implication of observations are the following. So if we use the latest observations, particularly after the BICEP 2 to 2018 BICEP Keck array results, the paper came up in, I think, last year, 2021. This is the scenario. Here is where the observation is. This is scalar spectral index, and this is tensor to scalar ratio. And this is an important bound that the tensor to scalar ratio is smaller than 0.036 at 2 sigma level. And the scalar spectral index has both upper and lower bounds. Okay. This actually rules out a huge class of models. All convex potentials are ruled out. Not only that, the whole family of monomial potentials, phi to the power p, where p could be greater than 1 or smaller than 1. The whole family is ruled out. But there are some other models which are consistent with the data. Some of the models we discuss in the paper, basically. But today, I'll not focus on typical models. I'll give a general constraints in this talk. So the general scenario is that in single field slow roll inflation, the recent CMB data, they actually favor models that are shallow or asymptotically flat. So this kind of asymptotically flat potentials are favored over, let's say, a monotonically growing convex potentials. And the whole family of monomial potentials, P of phi goes as phi to the power phi, they are now disfavored by the data. Okay. We can also put some quantitative bounds on different parameters. So we take these two observational bounds, tensor to scalar ratio smaller than 0.036, and scalar spectral index lying in between upper and lower bound. This gives us, especially the tensor to scalar ratio, tells us that Hubble scale during inflation at max could be about 5 into 10 to the power 13 GeV, which is very interesting to know. So the space-time curvature during inflation, the Ricci curvature, is quite low compared to the Planck-scale. We can put bounds on the slow roll parameters. For example, the first slow roll parameter is smaller than 1%. And the second slow roll parameter, here I talk about eta v, not eta h, which is also quite small, but it cannot be very small because this combination determines the value of ns, and we know ns. So if future data puts epsilon h or epsilon v to be even smaller, eta v won't move much, it will just stay there to account for the value of ns that we have observed. The equation of state during inflation is very close to -1, as I'm showing here. Also, the field displacement during inflation, from the time when the pivot scale left Hubble radius all the way until the end of inflation, is kind of around 5 m Planck or so. Cannot be much greater than 5 m Planck. So these are very interesting general bounds on single field slow roll models that we obtained from this latest data. I'll talk about just one of the examples of one of the models which is compatible with data. This is the T model alpha attractor, which has a simple looking potential. It is tan hyperbolic to the power p into lambda phi by m Planck. You might usually see that there is alpha parameter which sits here 1 by √6 alpha, but I call it lambda just for simplicity. And depending on the value of lambda, this model could be compatible with the latest CMB data. Okay, so this is an asymptotically flat potential, and for different lambda, of course, the height of the potential will be different in order to satisfy CMB fluctuations. Here are the predictions. So as it turns out that in the large lambda limit, if lambda is large, these are the predictions of this model. Okay, so that there exists a attractor asymptote of this model where ns and r both go towards that attractor value. Okay, see, ns becomes completely independent of lambda while r depends on lambda. So as you increase lambda, r becomes lower and lower and lower. So this is the attractor solution. I would like you to remember this plot because we'll contrast it with another plot in a while. So this is an interesting model. There are other models which are discussed in the paper, which I don't discuss here. So this is the picture of canonical single field models. If we go to non-canonical inflation, particularly Lagrangians of the form x into x to the power alpha minus 1. So basically x to the power alpha, where alpha is a parameter greater than or equal to 1, and x is just the kinetic term. We can write down the density and pressure and equation of motion of scalar field for this such kind of Lagrangians, which are not particularly illuminating for this talk. What is important is that we can study monomial potentials in these non-canonical scenarios. Okay, and we can compute slow roll inflation. So these are monomial potentials. V of phi goes as phi to the power p. These are ruled out in the canonical scenario. I'll show you what happens in the non-canonical scenario. We can derive expressions for ns and r. Again, not particularly illuminating here. But what I want to stress is that there is a consistency condition which is slightly different from the canonical picture. So this could be used as a smoking gun test. The second thing what is important is that in the limit alpha much greater than 1, alpha is the parameter in the potential which appears here. Okay, if alpha is equals to 1, it's a canonical picture. But if we go away from the canonical Lagrangian, alpha is much greater than 1, we get some kind of ns and r predictions which do not become independent of p. Okay, and they do not become independent of alpha. So we really don't have a asymptotic solution here. So to explain it better, I'll just show you the diagram. It looks very similar to the T model diagram. So this is phi 4, phi q, phi square, and all. They're all pulled towards the place where data is. So that's very nice. But they're not pulled towards one attractor or resign, but they're pulled towards different values. So there is no attractor asymptote in this case. So that's very interesting. I have plotted here a logarithmic curve for the same potential, and to just see that they become flat. So you can see that ns becomes kind of independent of this p, but r keeps going down and down as you increase alpha. Okay, sorry, ns becomes independent of alpha, not independent of p. Ns depends on p, but it becomes independent of the alpha parameter. But r keeps depending on alpha and keeps falling and falling. All these class of models, starting from phi to the power 2 by 3 all the way to phi 4th, they cover almost all of the range that is available in the data space, which is interesting. If we contrast this with T model alpha attractors, which also have kind of similar behavior, but they all go towards an attractor solution, which the non-canonical monomial potentials don't. So this is one of the most important results of the paper. In the remaining amount of time, I would like to discuss a little bit about I'll come back to the canonical inflation now, so we can forget about non-canonical, and we can talk about some of the issues of initial conditions that have been raised in the past 6-7 years, and there are some debates going on. One of the things that are told about plateau potentials are the following: that in the canonical picture, CMB data favors plateau potentials. We can ask questions that if the effective description of the scalar field begins somewhere closer to the Planck scale, slightly below Planck scale, at that time the energy density is closer to Planck scale, but potential energy is pretty low for these potentials. So that the equipartition of kinetic and potential terms could not be satisfied for these potentials. Second thing is, since the height of the potential is pretty low compared to, let's say, Planck scale, if there is a positive curvature present in the universe, then it will lead to collapse of the universe, as I will show a little ahead. Okay, so there is an initial positive curvature problem also. And the other problem had to do with how can we maintain the flat potential over a wide range of scalar field value, scalar field displacement. One of the ways to address this potential in form of a toy model that we proposed purely phenomenologically is what we call a Margarita potential. In Margarita potential, you have three regimes. So you have oscillatory regime, which gives you reheating. Then you have asymptotically flat for a while regime, which gives you CMB observations, or which can satisfy CMB observations. And then the potential might grow. How it grows depends on the details of quantum corrections. But in the paper, we have sort of discussed several types of modifications to asymptotically flat potentials, which gives rise to this growth, which could be algebraic or exponential. Here is an interesting prediction of NS and R for such Margarita potential curves. Okay, the red color curve is just T model alpha attractor, while the blue one is the Margarita potential, where the T model has been modified for large value of phi by exponential function. And I show here that we can see interesting differences between both the predictions, predictions of both the models, basically. If the modified parameter, exponential parameter, if it deviates too much, then of course this will lie outside the data. So there is a range of parameters which satisfies the data very well. This can address the issue of initial conditions quite well, because for plateau potentials, if you start initially with slightly high curvature value, which is still much an or lower than kinetic term, potential is quite lower, of course, then at some point universe goes into collapse. While for Margarita potential, even starting with more than one order difference, universe can actually bounce back and expand and inflation happen. So this is how it solves the initial condition problem.